My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today we want to look at mass flow per unit area. Mass flow per unit area. And of course that's in a duct. Remember, we are working with the one-dimensional steady flows. And remember, when we talked about one-dimensional steady flows in earlier lectures, remember that we characterize a one-dimensional steady flow as one where, for example, the change in the area and curvature of the axis was gradual, and that the mechanical and thermodynamic properties along the plane, which is normal to the axis of that particular duct, is constant. And so it's very important for us to remember those things. And in the other lecture, we also derived the expression for the velocity at state point 2, or what we can call at plane 2. So we say that C2 squared, where we had assumed that C1 was negligible, so the C2, that is the velocity at plane 2 at that state point 2, we said was 2n 1 minus n P1 V1 into P2 P1 n minus 1 over n minus 1. That was our discussion. And remember that n is the isentropic index of expansion in that polytropic equation which we had derived. Now, keeping this in mind, very important for us to remember that. We also talked about the continuity equation in terms of principle of conservation of mass, the continuity equation. So from the continuity equation, well, remember, we said we have A1, C1, V1 is equals to A2, C2, V2. That's a constant. And A, remember, was the area. C is velocity, and V is specific volume. So, this quantity here actually represents the mass flow rate. And how do we do that? Let's just look at dimension analysis, just to make sure that you are in line with what we are talking about. Let's just do some dimension analysis on this expression. Just basically using the dimensions. So, when we have A, that's AC over V. When we have A, that is like length squared. And C, we have said is velocity. So if we multiply that by velocity, that's length over unit over time. And this is divided by specific volume, which is volume over mass. And that is length cubed over mass. So if you cancel out these dimensions, then you will have length squared times length time multiplied by mass over length cubed. Of course, this will cancel out. We're left with mass over time, and that's the mass flow rate. So dimensional analysis is very important, especially when you are working in terms of deriving new equations to account for certain phenomena in thermodynamics or in any other field, whether it's fluid dynamics, whether it is in whichever field. It is very, very important for you to check your units. That they actually conform to what you are talking about. So when you say this is the mass flow, when you're talking about mass flow and you do your dimensional analysis and you don't get the expression showing you that is mass over time, which is mass flow rate, then in that particular case you'll have had to move in, probably put in a correction factor so that you harmonize those units with the expressions which you're deriving. So that's very, very important for you. So we are talking about principle of continuity equation there, and we have the expressions there. So we have mass flow rate is equals to A2 C2 over V2. So if we rearrange this expression, very simple arithmetic, on rearrangement, rearrange this quantity here, then so that we get the mass flow over area, mass flow per unit area, then we divide by area, so we'll have C2 over V2. So let's call that expression 1. So our lives are becoming a lot easier. Now we want to get the expression for mass flow per unit area. So what we need is to work with this quantity on the left-hand side, on the right-hand side, and see what we obtain. See what we are able to obtain. Now, we already said that C2 squared was 2n, n minus 1, P1, V1, P2, P1, n minus 1 over n minus 1. That was the expression which we had gotten in our previous discussions. And so basically C2 therefore is the square root. C2 therefore is the square root of this expression, n minus 1 P1 V1 into P2 P1 n minus 1 over n minus 1 square root. And we said that the maximum velocity, remember, we said the maximum velocity, for example, in an also is when the pressure is 0. When the final pressure is 0, so P2 is 0, then that expression will vanish. So that expression will vanish, so we'll have minus 1, and of course will be minus times these quantities which you can remove, so that we say that Cmax would be 2n over 1 minus n P1 V1. Remember, just recall, at maximum velocity, P2 will be equal to 0. Therefore, it means that Cmax, in that particular case, C2 maximum is simply 2n 1 minus n P1 V1 square root. And remember, this minus sign has taken care of that. That's why we have changed that denominator. So don't get confused over that. Now we know what C2 is here. Rho as it is. This is for maximum pressure. But we are interested in the rho C2 along the system. So we have the C2 there, which is this expression which we call 2. We can substitute there. Now the question is, what is V2? To compute the specific volume at state point 2, at plane 2, we will use the polytropic equation to compute C2, V2. We use the polytropic equation. And remember the polytropic equation, we said P1 V1 n is equals to P2 V2 n, and of course that will be equal to PVn. And that, as we had said, was the isotropic expansion. That's the index of isotropic expansion, asymptotic expansion. And then we had said that this n, in the case of perfect system behaving like ideal gases, that will be gamma, where gamma in that particular case will be the ratio of the heat capacities. That's the ratio of the isobaric heat capacity and the isochoric heat capacity. So if we pick out using the polytropic equation, therefore, what are we saying? We can say that V2 P1 from P1 V1 n is equals to P2 V2 n. We can say that V2 n over V1 n, that's just dividing, will be P. If you divide that with V1 n both sides, then you can divide P2 both sides again, will be P1 over P2. So I've just divided with V1 raised to power n on both sides and divided with P2 on both sides. So we have that expression. So removing this exponent, remember, don't get confused. Well, remember, just note the identities which you are using here. If you have x over y, the n that's simply x over y raised to power n. And similarly, the other identity which you want to use is x, y, the n is equals to L over m, can also be expressed as is equivalent to x over y is equals to L m 1 over n. In other words, you divide the exponent by n. So we are going to use these simple identities in mathematics to simplify this particular expression. Let's call that expression 3. So on simplifying expression 3, what do we have? We have V2, V1 will therefore be equal to P1 over P2 raised to power 1 over n. We've just applied the laws of indices there. We need that expression there. So, now our life is easy. Our life is very, very easy. So to get now the mass flow rate per unit area, we just obtain a specific volume at state point 2 by simply cross multiplying. Therefore, V2 will be equal to P1, 1 over n times V1. And so, let's call this expression number 5. So if we substitute expressions, if we substitute the expression for C2, which is the square root of that expression there, expression number 2, I think we have just erased it, that is C2 squared is equal, C2 is equals to 2n, n minus 1, P1, V1, P2, P1, n minus 1, raised to power half. So if we substitute this expression 2 and 5 into expression 1, substituting expressions 2 and 5 into 1, then we obtain our expression now for mass flow rate per unit area. That is M. Therefore, M, what are we saying? M over A2 will therefore be equal to C2 is 2n over n minus 1, P1, V1 into P2, P1, n minus 1 over n minus 1, and all this is square root. Let's clear some space here. And then, of course, we know what our V2 is. So divided by P1 over P2, 1 over n V1. So this purely, this expression 2, this expression 5. Very simple. So now our whole assignment here is to simplify this particular quantity. And one of the ways is to, because we are seeing we have the pressure expressions here and specific volumes, so we need to take them up and consolidate them into one expression. So M over A2, which is the mass flow rate per unit area. Remember, M over A2 is mass flow rate per unit area. Now, to consolidate these quantities, we have now 2n over n minus 1 P1 V1 into P2 P1 n minus 1 over n minus 1 square root times, when we take this up, of course, we will invert that fraction there. So we'll have P2 over P1 to the power 1 over n divided by V1. Let's not forget our V1. So we are getting there. Now we simplify it. And you're just going to use the simple identity. I'm going to use the simple identity. The square root of x squared is x. And so, because you have square root here, so simply, just like in a more simple term, square root of 4 is 2. So when I have this value here, pay attention. When I have this value here, I can bring it into the square root bracket by doubling its value. When I square this quantity, P2 over P1 raised to the power 1 over n times P2 P1 raised to the power 1 over n, that when I take the square root is basically P2 of P1 1 over n, which is what we are saying. If you have x squared, square root of that is x. Square root of 4 is 2. So in this particular case, what are we saying? We are saying that P2 P1 1 over n times P2 P1 1 over n. If I take that square root of that is the same as P2 P1 1 over n. But now, what has happened? What has changed there? What has changed there? So the expression, when I want to take this inside here, I will have to square it. And when I square it, now we'll use this law of indices, which we have used extensively. X to the n times x to the m is x n plus m. That's the identity you're going to use here now to simplify that. So we'll have P2 over P1, the 1 over n, plus 1 over n. And so that will be P2 P1. That will be 2 over n. So this 2 over n is what I put into the bracket where we have the square root. Therefore, m over A2, that's the mass flow rate per unit area, will be 2n over n minus 1 P1 V1 into P2 P1 n minus 1 over n, now times P2 over P1 2 over n minus P2 over P1 2 over n. That will be the value in terms of putting in that over V1. And so what happens here? What happens? We have now, this will be 2n, n minus 1, 2n, n minus 1, and then of course P1, V1, into P2, P1, let me put this a little bit up, V1, into n minus 1 over n plus 2 over n minus P2, P1, 2 over n square root over V1. You can clearly see now, it's easy to solve that particular problem. Now much easier. So what do we have here? So we have m by A will therefore A2, that's mass flow rate per unit area, is 1 P1 V1 into, if you sort out this particular index, we are going to have P2 P1 into N minus 1 plus 2 over N minus P2 over P1 2 over N square root, which simplifies further to 2N N minus 1 P1 V1 into P2 P1, that is N plus 1 over N minus P2 P1 2 over N square root, don't forget our V1 over V1. That is the expression for mass flow rate per unit area. And this is a very important quantity because now remember, at the throat, the mass flow rate is maximum. The throat, the mass flow rate is maximum. Note, at the throat, please, if you have not followed this, we have done it in one or two of the previous lectures where we have drawn even the schematic of the throat. So at the throat, the mass flow rate per unit area is maximum. And therefore, if we take the derivative of this, we are going to be able to get the pressure at that particular point. And that will be the subject of our next lecture. Let's meet next time as we continue.